Today we're going to look at the last case in which we can use the law of sines to solve for unknown parts of an oblique triangle. First, let's start the Edmodo quiz by doing an example using the information that we learned in the previous video. What I'd like for you to do is to use the law of sines to find the unknown values. Given that you know angle A, angle B, and side C, you will first have to find angle C, then use the law of sines to find side A, and then repeat the law of sines to find side B. The first three questions in the Edmodo quiz correspond to these parts of the triangle. Just pay close attention to which part you're answering for which question. Go ahead and pause the video now, solve for those unknown parts, and enter them into your Edmodo quiz. You just completed a situation where you knew angle, side, side, and were able to use the law of sines to find all of the unknown parts. Yesterday we also looked at examples using angle, angle, side. These are in essence the same thing. Once you know two angles, you can easily find the third angle in a triangle, and then knowing one side allows you to use the law of sines twice to find the other two sides. Today's situation, angle, side, side, is very different. Angle, side, side should jog your memory from geometry because it cannot be used to prove that two triangles are congruent. Today you'll find out why. In trigonometry we call this the ambiguous case because it is ambiguous as to how many triangles exist with the same angle, side, side measurements. These diagrams explain the three different possibilities given an angle side side measurements. In this case, angle A is fixed for each of the diagrams, angle B is fixed for all of the diagrams, and the next given side you will have is side A. But notice that the three diagrams have different lengths for side A. These represent the three different ways in which an angle side side given part could manifest itself. Let's look at figure 2 first. It's probably the easiest to understand. Imagine that side A is just long enough to connect and create this vertex at B, which would be perpendicular. It would be a right angle. Now clearly in this case there can be only one triangle with that angle A, side B, side A measurement. However, if A was slightly different, that side would connect differently with the side between points A and B. Look at figure 3. In figure 3, again, same angle A, same side B, but this time the side A that we're given is much shorter. It cannot connect, it cannot reach down to this side to create a triangle. As a result, no triangle could have that combination of angle A, side B, and side A. Look back at figure 1 now. Same fixed angle A, same side B. This time A, the side, is longer than it was in figure 2. And so it definitely connects with that third side of the triangle. However, you'll notice that it could connect in two different places. It could create an obtuse angle B, or it could connect and make an acute angle B. Those two angle Bs are supplementary angles of one another. Depending on the length of that third side A or second side A, you could have anywhere between 0 and 2 triangles with the same angle side side. That's why you couldn't use angle side side to prove congruency in geometry, because angle side side could determine more than one triangle. Let's look at an example of this two triangle situation. Here we're given angle A of 60 degrees, side C of 10, and side A of 9. I'm going to set up the law of sines to find angle C, since that is opposite the other side that we know. I'm going to put the angles in the numerator of the law of sines, since that's what I'm looking for. So it's the sine of A, 60 degrees, divided by 9, equals the sine of C, the unknown value, divided by side C, which is 10. Just like before, I'm going to solve for my unknown value. This time, however, the unknown value is embedded in that sine function. So we have to use an inverse sine to find the angle. You're going to have to go to your calculator for a lot of these. The sine ratio, we're trying to find the angle that has the sine ratio that's inside those parentheses. When you use your calculator, you find that the angle is 74.21 degrees is equal to C. Now we're going to use that on the next page to see why we actually have two different triangles. Recall from our discussion of inverse sine functions that the angles that come out of inverse sine functions have to be in the fourth or second quadrant, somewhere between negative 90 degrees and positive 90 degrees. Well, there are angles in triangles that can be between 90 and 180 degrees that don't come out of inverse sine functions. So we're missing all of these angles over here. Luckily, it's pretty easy to find out that possibility. Remember that supplementary angles have the same sine value. As an example, 30 degrees has a sine of 1/2. Its supplementary angle, 150 degrees, also has a sine of 1/2. So we could look at the supplementary angle of 74.21 as the other possibility for this triangle. That angle is 105.79. So now we have two different triangles. Two different angle C's indicate two different triangles. So let me solve for the other parts of the two triangles separately. The third angle B can be found by subtracting the two known angles from 180 degrees. A is 60. The first possibility for C is 74.21. So that means angle B in the first triangle is 45.79 degrees. In the second triangle, angle B can also be found in the same method, but you're just using the other possibility for angle C. In the second triangle, angle B is smaller, 14.21 degrees. Now we'll need to use the law of sines to find side B. I'm going to go back to some of the information that we were originally given, side A of 9 and angle A of 60, to find side B using that new angle that we just found. So 9 times sine of 45.79 degrees over the sine of 60 degrees is equal to B. So for the first triangle, side B is equal to 7.45 units. We repeat this same process to find the other possibility for side B, this time using the angle of 14.21 degrees. When we solve for B this time, we should get a smaller side measurement as well. Since the angle is smaller, the side should be smaller, and we do get that. 2.55 units is the other possibility for side B. So, given angle A of 60 degrees, side C of 10, side A of 9, there are two different triangles that have those same measurements, and these answers show those two different triangles. With the last example in mind, it's now time to answer the fourth question on your Edmodo quiz. What type of angles have the same sine value? Complementary angles, obtuse angles, right angles, or supplementary angles? Pause the video, answer the question, and then restart the video. So let's see what happens mathematically when there's a situation where no triangles could exist. This time we're given the same information, angle A of 110 degrees, side C, and side A. Now, when we start setting out the law of sines to find angle C, we would say the sine of 110 degrees divided by side A, 125, is equal to sine C over the side C of 200. Isolate the unknown value. And again, we're going to need to use the inverse sign to find the angle. Now, I'd like for you to practice this. Type in exactly what I've typed in or written here into your calculator, the inverse sine of 200 times the sine of 110 degrees, all divided by 125, and see what happens. You'll notice that it gives you an error, domain. The reason why it says domain is that this ratio that we're putting into the inverse sine is greater than 1. As a result, it's not a valid sine value. It means that no triangle could exist with these dimensions. If we look back at what we were given, this will make perfect sense. A is an obtuse angle. That means it's the largest angle in the triangle. That means it has to be across from the largest side. But look, side A originally was supposed to be smaller than side C. The obtuse angle must be across from the largest side. And this is a case where you see both mathematically and geometrically that there cannot be a triangle with this angle side-side measurement. The nice part about using the law of sines to find the ambiguous case is that it usually tells you how many triangles there will be. In the last example, an error told us that there was not a triangle. In the first example, we got an angle and there was a supplementary angle that could have also fit into the triangle. That meant that there were two. There will also be situations in an ambiguous case where it determines one right triangle, and again, one of the angles that you find will be 90 degrees, and it'll indicate that that's just the one triangle. At this point, I'd like for you to look at a two-triangle example. I want you to find the two possible measurements for angle B. So that's the first step here, since you know side B, side A, and angle A. Now, you will be asked to enter both of these answers into the Edmodo quiz. It asks for the smaller one first and then the larger one second. Make sure you put them in the right order. This concludes the video. Go ahead and answer question 5 in the Edmodo quiz, and I'll see you tomorrow.